Okay. Good afternoon, everyone. We have something a little bit different to start today. You may have noticed we have a couple of guests here. I've invited them to come over just to talk about a flu study that they're doing, and they are looking to recruit public health students into this study. So I'm going to let them start by talking a little bit about it. This is Rumi, what was your last name?
Chinara.
Rumi Chinara from NYU. And I'm just going to hand the microphone over to you and maybe let you tell them a bit about the study while I continue getting the lecture loaded up here.
Sure. If I wanted to show our video online, can I do that?
Yes, we can do that.
Perfect. Thanks. Okay, so maybe I'll just talk and then I can pull it up.
Yeah.
Online. Okay, wonderful. Hi, everyone. Thanks so much for having us here today. My name's Rumi Chinara. I'm a professor at NYU at the College of Global Public Health and also in computer science. And Sophia is also here, who you'll meet, and she's project manager for our project called Go Viral. So you might be thinking, what do we do that's across computer science and public health? Well, we try and use a lot of data from the community into public health surveillance models and epidemiological models. Has anyone ever heard of tracking the flu on Twitter? Yeah, so you might have heard people doing this type of thing. We've kind of grown different studies out of that, trying to get more specific information from the community. So not just looking at passively mining data from Twitter, but also getting participatory reports from individuals about how they're feeling, what types of symptoms they have. And then also beyond, because when you have symptoms that are like influenza, it could be the flu, it could be a cold virus. So we actually have these kits that we send people if they sign up for our study from wherever they are around the city. So they have it at home, and if they get sick, they'll send us a fluid specimen. So it's not as gross as it sounds. I'll show a little video for our study. It's all online, and it would be really amazing if folks in this class wanted to sign up because our study allows you to track your symptoms on a weekly basis. So even if we know if you're sick or not, we have a sense of how many people are well. And then if you get sick, we get a result about what type of virus there was. So that's kind of very interesting. And we could also have you as a data point in our data set for the class, for example. And so we could see from this class how the season progressed, if anyone got sick, if multiple people got sick, was it the same type of virus or was it different viruses? So it's kind of a cool exercise for the class also to be part of that data set. Let's see, I just wanted to, I brought a couple giveaways just to get people a little bit excited about our study. It's called Go Viral. It's a very fashionable t-shirt with our logo. You'll see it in the video I'm gonna show also. So I just had a couple questions for public health type students who might know a little bit about cold and flu because it happens every year, especially in urban areas like New York City. Does anyone know what types of viruses besides influenza people get affected by in respiratory season? So if you have a cold, does anyone know what type of viruses could be there? And these will all be in the panel that we'll test your specimens for. Yeah.
Coronaviruses?
Coronavirus is very common. I think you're probably a little bit, I'll give you not this small one. So that's awesome. Yeah, coronavirus is very common. In fact, last year, most commonly when people had flu symptoms like a runny nose, fever, cough, it was a coronavirus here in New York City. A smaller proportion of those are actually influenza, so different types of coronaviruses. Now, why are we actually getting data from the community instead of looking at what happens through Sentinel sites, doctors' offices, hospitals? Because obviously they collect very robust data as well, but who comes in and they do some testing. Does anyone have a guess about how many people who, from our studies and other, who have gotten sick with some type of cold or flu actually go in to see a doctor or go to a hospital? And you can think about your own experience. If you get sick, what's the likelihood that you'll actually go in to see a doctor? Yeah.
Probably not, unless the symptom is progressively, getting really bad.
Yes, it's most likely that people don't. And do you have a guess for what proportion of people, like what percent of people who get sick go in?
20%. 20%?
20% is actually correct. So we find about consistently our study, other studies in the US, in different countries in Europe, about 80% of people who get sick don't go in. So that's why it's really important to do this study, because we're capturing data that it just doesn't get captured otherwise. Okay. Any questions so far? Just kind of explaining what's happening. Yeah.
Does it matter if you got a flu shot or not?
It doesn't matter. We ask for vaccination status because as public health students, you can understand that when you get a flu shot, it's very good to do that. It helps the community. It may or may not protect you individually from this year's flu strain, just because it's a guess, right? And so we find that we can get some estimates of vaccine efficacy based on our data, because we see exactly what type of virus people had. Yeah, that's so we do capture that information also. Okay, why don't I show the video, which might stir some other questions, and then we'll let your class proceed, and during the break, maybe we'll help you guys sign up, and I'll just show the website and video right now also. Okay.
What is the
goviralstudy.com. So this is where you'll go if you just want to sign up.
share my screen here?
So for folks who are watching this online also, it's very easy. You can go sign up yourself. And if you're not in class, we actually usually mail people the kit. So it'll come to you in the mail. But for folks who are here, it's really easy. We brought them here for you to just grab in person. So if you just actually scroll down a little bit, so you can sign up. We have a little bit of information about what's happened in previous years. And then this is the introductory video I thought would be good for us to all watch.
All right. Thank you, Rumi. And one thing that she mentioned, which was especially interesting to me, is their willingness to share the data from our class with us, anonymized, of course. But I'm having this class. She's coming into this class and also my BIOS 2 class, and I'm looking forward to hopefully having enough people to have a data set so that we can use in future offerings of this class, and maybe when you guys take BIOS 2 next year. Kind of fun to analyze our own data. So if you're interested, please do go ahead and sign up. And yeah, if you guys would stick around for the break.
Yeah,
Then
we'll stick around, and then when you're the break, I'll just show the sign-up sheet on here,
okay.
and then we can give everyone a code so that we know you're in this class, and we know which data to pull. We can do that. We can pull that data later on.
Okay. Thank you.
Thanks.
All right. Okay, we're moving on today to sampling and sampling distributions in the central limit theorem. Everything up to this point has been about descriptive statistics, about data, and about probability. And today we're going to lay the foundation for inference, which is what we'll focus on for the rest of the class. I'm going to start, it's been a few weeks now since the last class, so I'm going to review the stuff that we've covered around populations versus samples and use that as a springboard into from the sample to sampling distributions, and talk about the central limit theorem from there, which provides a basis for many statistical tests, and then talk a little bit about ways of collecting data, experimental versus observational studies, and prospective versus retrospective. So we're calling this example of the state of Massachusetts just because I had a nice infographic for that. The population can be a statewide population, countrywide, subsets of it, as long as it is a well-defined population for which we can enumerate who is a part of it and what are the parameters involved in someone being a part of that population. And samples are randomly selected from that population and generally selected in more manageable chunks of some number of people for whom we can collect data on and do analyses on, because it is normally not practicable to study the entire population, except, for example, in a census. And remember, we've been using the Roman letters to describe sample data about the sample, and Greek letters to describe things about the population. And in general, inference is about taking data from a sample and inferring things about the population based on what we see in that sample. A little bit of vocabulary. The study units or the sampling units would be the individual elements of interest, often a person, but it could be something other than a person. It could be a school, it could be a neighborhood, but it is the smallest unit at which we are collecting data. The target population is the idealized population that we are trying to make inference about based on our sample. And the study population is who we are actually sampling from, which ideally would be the same as the target population, but if there are some individuals in the target population whom are excluded from sampling, then they may differ. And those kinds of systematic differences introduce selection bias. And finally, the sampling frame is just a list of all of the units in that study population, and this is required for random sampling. Whoops. So again, we're using Greek letters for population parameters and the English alphabet for sample statistics. And I use the word statistic to mean that it's a description, something calculated from the sample, and a parameter for something that is calculated for the population. There are numerous ways, strategies for sampling from the population. The one that we'll be concerning ourselves with in this class is the simple random sample. And this is the most straightforward to design and to analyze. There are good reasons to use other strategies, but this is your basic strategy where everyone in the population has an equal probability of being sampled, and it is random. So if there are 1,000 people in the population and you're selecting 10 people, then every individual has a 1% chance of being selected. It's the same for everyone. That's all there is to it. That's a simple random sample. Systematic sampling would be an approach where you have your records enumerated based somehow, and rather than randomly selecting from that, you take a systematic, for example, every record that is divisible by 3, something like this. Of course, if you're doing this, it depends on how your population is ordered, but there are certain cases where it makes sense, as I'll show with geographical samples. This approach can make sense. Stratified sampling is a way of improving or assuring the balance of certain elements of interest in your samples. So rather than giving everyone an equal probability of being sampled, you can do things such as ensure a particular age representation in your sample by first taking a random sample of people who are from 20 to 29-year-olds, and then another sample of a given number in the 30 to 39-year-old range. So it is still a random sample, but you are drawing your random samples within strata so that you guarantee a particular representation of those strata. And this is a good way of reducing sample variation when you have strata that are important to your study. Cluster sampling is often a two-stage or multiple stage sampling process, and it is where you have where your individual records occur in clusters. So a classic example could be schools, where you have, say, 200 schools in the city, and then you have some number of students in each one of those schools. A cluster sampling strategy would be where you first randomly select some number of schools and then randomly sample the students within those schools. So rather than giving every student across the city an equal probability of being sampled, you're doing this in 2 steps, where you only select certain schools and then sample students within those schools. So a good reason to do that would be if you're studying an intervention at the school level where it has to be applied to an entire school or not applied. Or if it is simply not practical to go around to all 200 schools, you need to focus your efforts on some more limited number of schools. And this is something you will also be learning about later in your degree. And then there are so-called non-probability samples, where you are relying on volunteers, patients who come into a cancer clinic, or other kinds of convenient samples. These, of course, are prone to selection bias, in that the individuals who are willing to volunteer are systematically different than those who are not willing to, or they don't represent all of the target population. But in spite of that, they are often the only way to do studies. Well, we'll talk about this later. So I just wanted to give an example here in a geographical study. So here is a map where this area has been broken up into equal squares, and so these squares constitute our records. A simple random sample would be here, where every square has an equal probability of being sampled, and you see, some areas get less coverage, some areas get more coverage. So that may be, that it is a valid sampling strategy, but you do end up with a fair bit of sampling variation and a lot of coverage in some areas and not much in another. The systematic sample guarantees an equal representation throughout the entire area, and it is still a random sample if there is randomness involved in your starting point. So every block then has a known and non-zero probability of being sampled. The stratified random sample could be where, say, we define the area above this river here and the area below this river as separate regions, and we select a desired number of plots from each of those. So that way you eliminate the variability in the number of samples you get from each of these regions, although it's still a random sample. And here's one example of a non-probability sample where, I don't know, we're taking samples along either maybe this is a road where it's easy to get samples from, and a site here where for some reason we take samples. So what would you call the go viral study? Yeah, it's non-probability sampling. But I mean, in general, probability samplings and study like this are very expensive to do. So I imagine you would face the choice if you wanted to do a probability sample of New York, you would be paying 10 times as much to get the same sample size, or be getting a much smaller sample size to do the same thing. Some studies like the New York City Haines, the National Haines study are probability samples, and they're very expensive to do. So here is just an example of a population. This is the Run Pen data set, which is available as it's a common data set for statistical teaching, but it's all about 17,000 10-mile participants from this DC Blossom Run in 2009. So you could ask first, is this a sample or is it a population? Yeah, well, I guess it depends on how you're going to consider it. If your target population is the 2009 DC Cherry Run, then it's the population. And probably if you're doing analyses on some subset of that, you're going to be assuming that is your population. You could also think of it as a sample if really your interest was in all 10-mile runners or all the years of this competition, and you considered this to be somehow a representative sample of some larger number of runners. So these are running times, and the frequency in this population of 16,924. And if I take a random sample of 100 runners from that, you see that it pretty closely resembles the population. It's not exactly the same, but the shape of it is the same. The center is around 100 minutes, and it has the same bell kind of curve. So the individuals in this population, because I have randomly selected it in this example, are more or less representative of all of the runners in this big race. what is a sampling distribution? So what I just showed you, it was the distribution of individuals in a sample. That is not a sampling distribution. The sampling distribution is the distribution of something calculated from a sample like that, observed then over many samples. So an example of how you might generate a sampling distribution would be to take a sample like that 100 runners that we saw, calculate a sample statistic from it, let's say the mean, and then repeat that over and over. This is a frequentist definition of a sampling distribution. It's generated over large numbers of samples. And then the distribution of those means over many, many samples, that is the sampling distribution. So if you take a moment to think about that, in our study or any study where you collect just one sample, which is what we usually do, one sample or two samples in a study, you are not observing the sampling distribution. You're only getting one observation from that sampling distribution. So this is an important thing to keep straight in your mind. There is a population distribution, and remember that the individuals in this sample more or less mimic the population distribution. This is not the sampling distribution. We're going to learn more about the sampling distribution today, but it is something that you will never directly observe unless you're doing a simulation on a computer. And these sampling distributions are different. Here's an example of a normal population distribution. So with a mean, this is serum cholesterol with a mean of 211 milligrams per 100 ml of blood, and a standard deviation of, I don't know, about what is this, 6 or 7, something like that. This is the distribution of serum cholesterol levels in the population. If we take samples, so a group of people, take the average of those samples over and over, the sampling distribution is going to look different. It's going to be more pointy, like this, so a narrower distribution. That's the key point. And this makes sense, right? Because you kind of expect that the average property of groups is going to be less variable than individuals. You know, if we look at the average characteristics of entire classes, they're going to be less variable than the individuals in those classes. So going back to this example of the 16,000 runners, where with a median of 33, mean of 36, standard deviation of 10, and then looking at the 100 runners, and I've already given this away to you, but is this an approximation of the population distribution or the sampling distribution? This is a sample of 100 runners. Sampling, yeah. Or wait a minute. Is this an approximation? Does this look like the population distribution, or does this look like a sampling distribution? It looks like the population distribution. It's got the same peak here at about 30, has about the same spread between about 20 and 70. We have a little less up here just because there are fewer extremes in the small sample, but it looks a lot like the population distribution.
Like 100 samples of them.
That's right. If we were to calculate the mean of this and then take 100 samples of that, that would be a sampling distribution. So this, even though this is from a sample, this is not a sampling distribution. Yes?
Usually when you look at the labels, if it says mean of something, that would be a sampling distribution.
Well, I wrote the mean here. This is mean equals 35.
Right.
It has a mean.
Right, but I said like the reason why this cannot be a sampling distribution is because the x-axis is 1 or h.
instead of
Right.
mean age,
Exactly.
runner mean age. Yep, that is a way you could tell that it is not a sampling distribution. Also, just from my description, this is 100 runners. This is not, you know, the means of 100 samples, something like that. Everyone clear on that? Why this histogram is not a sampling distribution? Okay. So yeah, this mean of 35 would just be 1 point on the sampling distribution because it's a single sample. But these distributions, the population distribution and the sampling distributions, are related by the central limit theorem, which relates the population distribution and the sampling distribution. There are 3 components to it. The first is that the mean of those 2 distributions are identical. You want to guess, so why do I say identical and not just close? Because in sampling, there's like random variation, right? If you take another sample, the mean is going to be a little bit different. So why do I say they're identical? Really identical. Yep.
You assume your sample is representative of the population?
Yep, you assume your sample is representative of the population. So under that assumption, why can I say that they're identical?
They have the same mean.
But that's circular. So why is the mean the same? Identically the same, not just close. It's the law of large numbers. So the sampling distribution is built from a very large number of samples. So any one sample will have a distribution, or will have a mean something sort of close to the population mean, but it'll differ from sample to sample. As we calculate the mean of a bunch of samples, the more samples we take, the closer it will get to the population mean. And as we get to an infinite number of samples, they will be identical. And that is the sampling distribution is calculated under an asymptotic approach to an infinite number of samples. Right? It's not an infinite number of individuals in each sample. It might be 100 individuals in each sample, but it's an infinite number of samples. The second part of the central limit theorem is that the standard deviation of the population and of the sampling distribution are related by this equation. And I call the standard deviation of the sampling distribution the standard error. So it's still a standard deviation, but it has a special name. It's the standard error. And we only use that for describing a sampling distribution. This is something I have seen endless confusion over in public health, is like, should you report standard error or standard deviation? What's the difference? A lot of people say, well, I report the standard error because it's smaller. Well, they're different things. They're describing 2 completely different things. The standard deviation is telling you about the variability of individuals in the population. And even if you calculate it from your sample, it's still approximating the standard deviation in the population. The standard error, what is that approximating? Yep.
Is that the standard deviation from the sampling distribution?
Yeah, it's the standard deviation from the sampling distribution. So it's the variability of the sample means. It tells you how much you expect those means to vary as you take repeated samples. So it's related to your uncertainty in the mean of the sample. And it's related just by dividing by the square root of your sample size. That's it. And the third part, maybe the most surprising, is that for large n, so for large enough samples, the shape of your sampling distribution of the means becomes normal, and it doesn't matter what the population distribution is. So if your population distribution is uniform, let's say we're talking about, I don't know, about ages in an elementary school where we have equal numbers of students in each grade, so the distribution of ages is uniform between 6 years old and 12 years old. If you take samples, calculate the mean of those samples, then as the size of those samples get larger, it looks more and more normal, even though we had a uniform distribution to begin with. And in fact, for a large enough sample, it makes no difference what the distribution of what we're observing for the records is in the population. It can be skewed, it can be bimodal, it can be anything. It doesn't matter. The sampling distribution is normal with the same mean as the population and a standard deviation is equal to the population standard deviation divided by the square root of n. So just summarizing that, for a random sample of size n, the sampling distribution of the mean will have the following distribution. It'll have the same mean as the population. It'll have a standard deviation, which is the standard error of the population standard deviation divided by the square root of the sample size. And for a large enough sample size, it'll be normally distributed. So this standard error, by dividing by the square root of n, reflects the fact that the larger your sample size, the less variability there is in these means. So for a sample size of just n equals 1, the standard deviation is the same as the population. The larger n is, the less variable those samples are. So as you take a very large sample size, you're going to see almost no variation in whatever it is you're observing if you're taking random samples. And what do I mean by a large sample? Well, there's no real cutoff, but sort of as a rule of thumb, we consider if you have a sample of n at least 30, the central limit theorem holds pretty well. And especially if your population distribution looks anything at all like normal or uniform, then your sampling distribution will be very normal by the time you're at n equals 30. Only for some very extremely skewed distributions would you see any variation beyond n equals 30. So I'm going to be covering side by side with this and a few other classes. We'll talk about continuous data, in which we're going to use the standard deviation and the standard error to do tests with for inference. And alongside each of them, I'm also going to talk about proportions, because the sampling distribution of a proportion can also be approximated using the central limit theorem with the slightly different calculation of the standard error. So the things that we will use are, instead of the mean, it will be the proportion. So if we're talking about a binary variable, say the fraction of cases. So we have a case control type of study, not a case control type of study, but where we are observing a sample and reporting whether they get the flu or not. Then the p hat here is the proportion that have the flu. If it is 10%, then this is, in our sample, 0.1 times 0.9 divided by the sample size. And that gives us our standard error on this proportion. So it tells us if we were to take additional samples of that same sample size, how much that proportion would vary on repeated sampling. We can use this central limit theorem. It's very practical for inference. And for starters, so we've learned about the standard normal distribution. We know from the central limit theorem that if n is sufficiently large, regardless of the population distribution, then our sample means minus the population distribution divided by the standard error is going to be z distributed. So it'll be standard error, standard normal, zero mean, because we know that the sampling mean and the population mean are identical, and unit standard deviation, because we're dividing by the standard error. So for large enough sample size, this entity will have a standard normal distribution, and that allows us to calculate probabilities of observing a sample mean that we observed under random sampling. And we can use that to test hypotheses about what the population mean mu is. And you will get plenty of practice to get used to this, but that is the basic idea. You're going to have a hypothesis about mu. You're going to have an observation of the sample mean, and from that you're going to calculate the probability of observing something like what you did on the mean under the central limit theorem. That's hypothesis testing. You can also use it for confidence intervals under the same idea. And the idea around confidence intervals is that for a given sample where you calculate x bar, that is your best estimate of the population mean. But we know from the central limit theorem what the sampling variability would be under repeated sampling, and you can use that distribution from the central limit theorem to calculate in what interval you expect 95% or whatever percent of your samples to lie, to give a confidence interval around the population mean. So just to wrap up, the central limit theorem forms the basis for t-test, z-test, analysis of variance, and the confidence intervals that we're going to be covering for the next several classes. And it tells us that for large enough n, you don't even need to know the population distribution. That large enough depends somewhat on what your population distribution is, but beyond n equals 30, it's a pretty safe assumption that you can use the central limit theorem. So I'm going to wrap up here with also just a bit about experimental and observational studies, different ways of generating data, different interpretations. The key aspect of an experimental study is that there is intervention. So you're not just observing individuals from the population, you are actually randomly intervening on some of them. This is what randomized controlled trials are, and it eliminates the possibility of confounding because you control the assignment of your treatment or your intervention randomly, and you know what those probabilities are. So because you eliminate the possibility for other things affecting your outcome because you are randomly assigning them. You can prove causality in experimental studies. In observational studies, there's no intervention. There are several types of these cross-sectional studies, such as the ones I mentioned, NYC Haynes Behavioral Risk Factor Surveillance System, the National Haynes Study. These are a cross-section of the population at a given point in time. And they're just observing, asking questions, taking measurements. This, by the way, is what how we would categorize the Go Viral study. In retrospective studies, you recruit people based on their health status. So this would be, say, you interview people, you ask whether they have had the flu in the past year, and you recruit cases, controls based on past health status. And prospective would be where you follow up a cohort through time, which actually maybe is a better description of this study because you'll be followed through time throughout a flu season. Observational studies in general cannot prove causality because you're not intervening. There is a possibility that that there are other unobserved things influencing the outcome that you're observing. So even though you observe people with different outcomes, with different exposures, there may be other differences that you're unaware of. Just as an example, does smoking cause lung cancer? If you wanted to address this directly by an experimental approach, you would have to intervene. So one way you could design a study like that, it would be to take never smokers and randomly assign them to smoking and non-smoking groups, follow them over a number of years and see which group develops more cancer. This would be a very direct way of observing it. It's never been done because obviously that's not an ethical study to do. An alternative experimental approach could be to take smokers and assign them to no intervention or to a cessation program and follow for years to see who develops more lung cancer. That, of course, is going to have an element of observation to it unless your cessation program has 100% efficacy and your smoking group, everyone continues to smoke. So this, in many important public health program questions, there has to be an element of observational study to them for practical and ethical reasons. Alternative observational approaches in that same example, the cross-sectional approach would be to take a sample of the population. So, and this has been done every year in the studies that I mentioned, ask whether those individuals have been diagnosed with lung cancer in the past number of years, and also ask about their smoking status and see if there's a correlation between them. The retrospective approach would be to recruit some number of cases with lung cancer, some number without, and then collect other data on them and their history and see if there are other differences between them. And the prospective approach would be to take a group of individuals, follow them over a number of years, collect information on their lifestyles and exposures, and then see over the years who gets lung cancer and see what differences exist between them. So obviously none of these are perfect because there is the possibility of there being other differences between the lung cancer and the non-lung cancer groups that you don't know about. But between a combination of them, you can start building up pieces of evidence. And I'm going to wrap up. Here's a summary just for your notes of the key things to remember from the class. We're going to take about a 10-15 minute break. If you would like to sign up in the study, these guys will be here to help get you started. And then after that, Tony will get started with the lab. Thank you. And for the online folks and for everyone, I'll also post a link to that study so that the online people can sign up as well. Thanks.